So, you might be asking yourself, what is calculus? What have I gotten myself into? So, I wanted to go over a broad view of what the course is, the big ideas, and kind of what we're up for, and some things to look out for as we work our way through. Okay, so I'm going to keep kind of sprinkling these in so that you have this conceptual understanding as well as the nuts and bolts of how calculus works as we go through problems together. So, calculus is called the mathematics of change. It's pretty widely considered to be the math of change. That's like a quick way to describe it, but it's actually pretty broad if you think about it. What changes? Well, everything that we care about changes. So to have math that describes how things change and we can analyze the patterns of change and these different behaviors, that's going to span different schools of study: biology, sociology, right, computer science, anything, engineering, obviously. So it's the math of things that change. And so anything that's interesting changes. And so calculus finds its way in to all these different fields pretty easily. And it's why it is a prerequisite for a lot of the higher level study of all different sorts of fields and disciplines. So what makes it that way, right? What makes it the math of change? One way to view it is something I'm stealing from Professor Strogatz at Cornell, who wrote a book called Infinite Powers. It's to think of calculus as the power of infinity. And I love this metaphor because what we're doing is harnessing this idea of infinity that's been kind of elusive for thousands of years, and mathematicians didn't want to touch it because they thought it was literally the devil. They thought it was evil. And because it's paradoxical, can we actually go to infinity? Can we talk about infinity in a meaningful way? And what calculus allows us to do, resting on the idea of the limit, which you might remember from pre-calc, and if not, we'll discuss it here. It rests on the idea of the limit of approaching infinity, whether infinitely small or infinitely far off in the future or infinitely far back, whatever it might be. It allows us to use this power. It all hinges on the limit to solve problems, okay, and then analyze how things change. So in two ways do we get to use the power of infinity. We get to use it in infinitely slicing complex problems into smaller pieces. This is what we call differential calculus, and that's the main crux of this course. The second way is adding up infinitely many pieces. And this is where we'll kind of leave off the course, is what we call integral calculus, integration, bringing things together. Will be the connecting piece to Calc 2. Calc 1 is differential calculus, so difference, slicing, subtraction. You can kind of see that a little bit. So cutting problems into infinitely small pieces, which are then easier to deal with. And so that's really how we use the power of infinity, which again rests upon the limit as the key idea. The limit is what we call the underpinning of calculus. So this really can't be understated how important that is. The last thing I wanted to say here is, these ideas, I'm explaining them pretty simply, and I think anybody could understand them who's had a little bit of math or maybe not even that much. So why is calculus so hard? Why do so few people take it? And it kind of seems to be like this barrier into higher level analysis of different sciences. The reason that it's so hard is, well, there's a few reasons actually. The first is that it requires a ton of algebra. Why does it require so much algebra? Well, calculus in itself is a simple idea. Its application is where the difficulty lies. Now that we've had this idea for so long, we're very concerned with equipping our students on how to apply calculus, not just the main idea of calculus. Okay, so in order to use these applications, we'll have to use a lot of algebra that you may not have used in quite a while. Kind of, older exponent rules, things, specific domains and ranges of specific functions, because we're going to be talking about all different sorts of relationships. With that, and the same as geometry, you might have, not looked at geometric proofs or laws in a while, the law of cosines, just all different sorts of things I know that it's probably been a while. We're going to review them on the fly. But it's kind of bringing all those things to bear that you've been studying K through 12 and a little bit beyond, all to this kind of applied way of using mathematics. So that's what makes it so hard. There are two big applications that we care about that tend to be the most challenging. One are called related rates, and the other is optimization. These are two ways that we apply differential calculus. Again, related rates just means things that are changing in a related way. So you've got two quantities that are moving simultaneously, so you can see how that'd be harder. And optimization, minimizing costs, increasing profits or efficiency, etc. That's a very general thing, and it's going to apply to environmental science, engineering, physics, all sorts of things, right? So that's really kind of what makes it so hard, is that not only is it calculus and we're going to introduce this new idea, but we're going to have to learn how to apply it in all different sorts of problems. And so we're all going to have different gaps on where we're comfortable. So as best you can, review things as we go. Make sure you're asking good questions, and you should be set. But this is an exciting topic, and you could probably sense my passion for this, because it's just a tremendous idea, and again, considered to be one of the greatest achievements of humanity. So I hope you're excited to dig in. We're going to jump in by looking at the derivative, understanding what rates of change mean on intervals, and then zooming in to instantaneous change. That's going to be the first theme before we get to applying this into these settings that I just relayed before. All right, so we'll see you in the next video.